Okay, let's get started. Uh, so in the last class, we first discussed the perceptron algorithm. So, and we found that like if the data set is linearly separable, then the perceptron will is guaranteed to give us some linear classifier which will be able to classify the data set correctly. And that means all the points belonging to one class will be on one side, and all the points belonging to the other class will be on the other side. But like as we also discussed, there can be multiple linear classifiers which are able to separate the two classes. Now, what do we like? And perceptron can give us any of them, but like we will prefer, or we will like to prefer such a linear classifier whose margin with respect to the given data set is maximized. That means that it is not only like it is not only enough to have be able to classify the all the points correctly, but the margins it should have with both sets of points, there is the plus one points and the minus one points. So the those margins we were denoting by gamma plus one and gamma minus one respectively. So and the total margin we called as gamma equal to gamma plus one plus gamma minus one. And we wanted to choose such a linear classifier W which will be able to maxim for which this gamma will be maximized. And why is that? Why do we want to maximize the margin? That also we understood with the help of an example, that if the margin is very small, that means that if there is a small change or perturbation in the measurements of any features, that means that corresponding data point will just shift a bit in the feature space. And then if the margin is small, then such a shift may take it across the across the classifier, or the across the linear classifier, which means it will become wrongly misclassified. So to avoid such risks of misclassification due to small changes in the feature values, so what I want is such a linear classifier which is sufficiently far away from both sets of points. So for that, we considered this kind of a situation. So let us say that there are some green points here and some red points here. The green points I'll call as plus one, the red points I'll call as minus one. So first of all, I will construct a marginal classifier. Any margin, let's consider any marginal classifier like this for the green the plus one points. That means it is like able to classify all of them correctly, but there is at least one green point which lies on that linear classifier. So the criteria for classification, for correct classification of these points is that, so for these points for which y equal to 1 or plus 1, so w plus transpose x should be greater than 0, or let us say greater than equal to 0. And for the other points which is y equal to minus 1, for them w plus transpose x will be less than 0. Okay. And similarly, for the parallel to this W plus, parallel to the linear, this marginal classifier, we will also have another marginal classifier for the red points. So like this, which will also again, it will call it marginal because it passes through at least one of the red points. So, however, not any of the red points will be beyond it. That is, all the red points will be either on this side or like or sitting on it, but not on that side. So for such points, we will have for y equal the points which are y equal to minus 1, we will have w minus transpose x is less than 0, or rather less than equal to 0. And for y equal to 1, the green points, for them w minus transpose x is greater than 0. Right? And if you see that will like the condition for correct classification is y into W transpose X should be greater than 0, right? That means either the that is like either both these and both Y and W transpose X, either both will should be positive or both should be negative. So here we can see that in this case both are positive, so correctly classified, and in this case also both are negative, so that also correctly classified. So similarly in this case like both of these are negative, so correctly classified, so their product is positive, and here also both are positive, so their product is also positive. So like if we choose the Y's and less, so like if this condition happens, then we can say that all the points have been correctly classified. Now we also wanted to okay, now for the like for the like to enable or to make our calculations a bit simplified, we have decided like we have made an assumption, that is we already know that W plus and W minus are parallel lines, that is we have chosen them accordingly. Now now we choose W, the actual linear classifier, which we will try to find as lying exactly halfway between them. That will ensure that their margin with respect to the plus points and the margin respect to the minus points are equal. That is gamma plus 1 is equal to gamma minus 1. So we define W as the half of W plus plus W minus, right? So this is the like the way we define W. We now for to help our the following mathematics, we just make another assumption, which is not really that necessary. The assumption is that like one of these lines, we will that is the one of the classifiers, the marginal classifiers, we will say, let's say W plus, we will consider its equation as W transpose X equal to 1. And the for the this one, that is to say the W minus, we will assume that its equation is given by W transpose X equal to minus 1. So, and since the actual linear classifier lies halfway between them, so of course it will be W transpose X equal to 0. Okay. So now, of course, like in general, we cannot guarantee that like these properties will hold. That is given a set of data points, we may not be able to find this kind of lines which separate the like I mean with this kind of marginal classifiers having this property. But then, as I said, we can always scale the points in an appropriate way so as to satisfy this, but it's not really urgent. This is just to help in solving the subsequent optimization problem. You will see that it's not a very urgent requirement. So now, so we are talking about the margin. So one margin is this gamma plus, and one margin here is this gamma minus. So here you can see that so we have two parallel lines. One of them is W transpose X equal to 0. The other one is W transpose X equal to 1, right? And so now we can use the formula of coordinate geometry to calculate the parallel distance between them, and it works out to be 1 by the L2 norm of W, where L2 norm of W is basically, as you know, the sum of the squares of all the like elements at the and root over of that. So that is the similarly this distance, this margin gamma minus, that is also W transpose X equal to that margin is also the same, which is 1 by the L2 norm of W. So the total margin is gamma 1 plus gamma minus, gamma plus plus gamma minus, that is equal to 2 by the L2 norm of gamma W. So now, like we have already decided that we want to maximize this margin. So I will have to choose W in such a way that this margin is maximized, and which in turn also means that if you just take its reciprocal, that reciprocal will have to be minimized. And to further like help in the mathematical optimization which follows, instead of taking the L2, the half of L2 norm, we will take L2 norm square. So just to do away with this root over term, we'll do the take the L2 norm square and try to minimize it. So our objective function becomes as follows. We are looking for that W for which this half of the squared L2 norm of W is minimum, but conditioned on the criteria that all these points are correctly classified, not only with respect to the the main classifier W transpose X equal to 0, but also with respect to the marginal classifiers. So like as you can see, the marginal classifiers are defined in such a way that they themselves can do the classification with the albeit that some points will be sitting on them, but no points will be misclassified with the with respect to the marginal classifiers. So based on that, we write this constraint for all the data points as the as our constraints of this optimization problem. So this constraint, so this is left as an exercise for you to verify that this constraint means that both the both of the marginal classifiers will be correctly classifying the points, or at least it will not be misclassifying any of the points. So these are our constraints. So it's like for every data point, there are capital number of n points in the training set. So each of like what we are saying is that each of the training points are correctly classified by the marginals. Okay. So, so this is the so now we can see that this is basically a constraint optimization problem. That is, we have to, there is a function which we want to minimize. That is, that function is the L2 squared L2 half squared L2 norm. But we have of course, so you can just say that if you consider the zero vector, that is W equal to all zeros, then of course this will have the minimum possible value. But that is not enough. I am not satisfied with just by minimizing the L2 norm of W. I want all the points to be correctly classified with respect to both the marginal classifiers. Okay. So for that, like the all zero vector which we just mentioned, for that this thing will probably not happen. That is, if W is equal to all zeros, then W transpose Xi for any given point, W transpose Xi will also have to be also have to be 0, right? And so on the left hand side we are getting 0, but 0 is not greater than equal to 1. So this constraint will not be satisfied. So we will not be selecting W equal to the all zeros vector. That will not happen. So we have to choose such a W for which the that is we will focus on only those W's for which this holds. So that we will call as the feasible set of W's. And then within that feasible set of W, I will choose the one for which this function, the squared L2 norm, is the minimum. Okay. So that is the optimization problem which we want to solve. Now let us see how to solve it. So we now in case of whenever we have a constraint optimization problem like this, so let us, there is a standard form for writing the solving the constraint optimization problem. So it's so this is the standard form of a constraint optimization problem. Minimize fx, or rather you can write as x hat equal to arg mean over x fx constraints gx is less than equal to 0. Okay. So if this like the if you have a form of like if you have an optimization problem of this type, then what we do is that we like this is the like we say this is the objective and this is the constraint. So in general, there can be multiple constraints like this. And like we can like take all of them together. We can actually write them as g1x less than equal to 0, g2x less than equal to 0, etc. We can even have some equality constraints like this, like h1x equal to 0. I mean, they have to be strictly equal. Then h2x strictly equal, etc., etc. So as of now, let us forget the equality constraint. Let us focus only on the this less than equal to constraints. So now what we are going to do is that we are going to like we already have an objective function. Now what we will do is we will absorb the constraints in the like into that objective function. That is what like instead of trying to make or trying to ensure that g1x is necessarily less than equal to 0 or g2x is necessarily less than equal to 0, what we will do is that we will try to make sure that g1x is as low as possible, g2x is as low as possible, and if that makes them less than equal to 0, then fine. So yeah, and if it still does not make them less than equal to 0, then we will have to understand that there is that no such solution exists anyway. That is, the feasible set is empty. So if the feasible set is not empty, then we will be able to find that is, we will be able to find a situation where g1x is also negative and g2x is also negative, and this fx is also as low as possible. So based on that, we define our augmented loss function in the following way. So let us assume that there are k number of like less than equal to constants like this. So we will we will just absorb them, as I said, into the loss function along with the loss function along with these things. So these this total expression, this is called the augmented objective. And these quantities, the lambda 1, lambda 2, etc., these are called the Lagrange multipliers. So now this so these are all unknown terms. That is, I do not know lambda 1, lambda 2, etc. So now earlier there was only one unknown term, x. Now there are along with the x, all these extra k terms, these are also unknown. So this the augmented objective is, it's a function of not only x but also of lambda, where lambda is the collection of like all these lambda k's. So we can consider lambda as a k dimensional vector. So like the original loss function, the original objective function was only a function of x. The augmented objective is a function of x and as well as lambda. So now what we have to do is that like x hat will be equal to that is, over all possible choices of lambda, we'll have to that is minimize this quantity, and that value of x at which this minimum is achieved, that is the optimal value of x hat. Okay, so I mean, it's of course not enough to choose just x. We have to choose a lambda also, but like ultimately we are not interested in the lambdas. We are only interested in x. So we will try to minimize this thing with respect to x, like across all values of lambda, and accordingly we will choose x hat. Okay, so for that we have the standard toolboxes are available, so we can like always do the usual way of taking the derivatives with respect to all the variables. So these guys, like, so basically we will get total k plus 1 number of equations like this. Okay, and we have k plus 1 variables also. That is, one is x and the other k are all the lambdas. Okay. And so this x in general, this can be a vector, but that's not a problem. We can do the vector differentiation. And then, so we basically will have a number of equations, that is our k plus 1 number of simultaneous equations, and which we will have to solve. So of course, now while solving these simultaneous equations, we may run into various issues, so that we will have to like solve as the or handle those issues as the need arises. But this is like the standard recipe for solving a this kind of a like constraint optimization problem. Now come back to the specific case which we were talking about. So in that case, we are interested in finding the
Sir,
W. Yes.
in this case, how the gi of x lesser equal to 0, that lesser equal to 0 part is taken care of? Like we are augmenting the constants into the loss function, but how is that part taken care
Right,
of?
right, correct. So basically, like when you are taking these things into the loss function, what you are trying to do is you are trying to minimize the whole loss function itself. So when you are trying to minimize the loss function itself, you will naturally also be trying to minimize each of these things. Because if this is not minimized, then like there is always a possibility that you can reduce. That is, you can always like change x so that this is reduced even further. But of course, there can be some of these constraints can be contradictory in nature. So suppose you find a situation where g1x is is high, but g2x is low, and so you try to reduce g1x. In the process, you find that g2x has become high. So these kind of situations can happen. So what we are trying to do is we are trying to achieve a balance between all these things with the help of these Lagrange multipliers. That's the whole idea. That's the reason why we have brought in the Lagrange multipliers. So like what we are trying to do is basically we are trying to make sure that all of these things are minimized or are reduced simultaneously. And if that kind of thing happens, as I said, that trying to reduce one of these constraints results in the other constant going up and so on. So to handle that, we have kept these Lagrange multipliers to make sure that even if it goes up, it will not go up by too much. So the lambda values will have to be adjusted accordingly. And so you can say that this is like a kind of a relaxed version of the problem. So so in general we cannot give a guarantee that all these constraints are exactly going to be satisfied. If we were to guarantee all of them are simultaneously satisfied, then that would have become a more difficult problem. So what we do is we try to make sure that all of them are as low as possible. And if that means they are all negative, then that's great. If they and it's possible that we will not be able to make all of them as negative, but a few of them may become positive also. That will simply mean that there is no feasible set in this case. That is, there is no value of x for which this like all of these are simultaneously satisfied. That can happen. But if it happens that there is a feasible set, that is like they all of them are going to be I mean there are some values of x in which for which all these constraints are satisfied, then there is a theorem which shows that this will actually help that to be achieved. Okay. So
So,
yeah.
sir, if the lambda values are negative, then G will be maximized, right?
So is right. So the like that so the lambda values are basically things which are trying to adjust these things. That is like as I said, the sole purpose of the lambda values is to make sure that the whole thing is as low as possible. Like it's basically as I said, the purpose of the lambda values is to make sure that in case there are some kind of contradictory constraints, like reducing one results in the increase of the one, then the corresponding lambda will have will adjust itself in such a way that even if it goes up, even if the G2X goes up, it will not disturb the overall sum so much that the overall sum will not go down, like will go up. So that is the lambda. That is the lambdas basically they can scale themselves in such a way. That is, the lambdas are kept flexible so that they can scale themselves in such a way that that is those things never go up. But anyways, but we will also like we keep some kind of constraints on the lambdas, like if the need arises. So we will see that. So whenever so if it is necessary, like for a particular situation when it is necessary to put some kind of a constraints on the lambdas, that also we will find a way to put. We will see that in later in this lecture itself. So as of now, let us try to just frame the minimization problem, which optimization problem which we have according to this thing itself. So what we are trying to do is we are trying to find that value of W, let's call that W star, which maximizes the margin. So which means arg min over W half of squared L2 norm. Right. So this is basically the like objective function which we are talking about. Instead of X, we are considering, let's say W. Okay. And the constraints are okay. So there are n data points. So for each data point, there is this is the constraint. Okay, that means that it is going to be correctly classified by both the marginal classifiers. So here we talked about k constraints. So instead here we have capital N number of constraints, where this is the number of data points. But we see that this is not a the less than equal to constant which we wanted. So we will write it in the form of the less than equal to constraints. We'll write it as 1 minus yi w transpose xi is less than equal to 0. Correct. So now it has gone to that form. So we can say that gix or gyw is equal to the a. Remember, the x here is present, but the x are the observations which we know. So the x as well as the y's, we can consider them to be constants. The variable is w. So giw is now 1 minus yi w transpose xi. Correct. So now we have got it in the standard form. That is, we have got the FW and we have the main objective function, and we have also got all the constraint equations, all the n number of constraints. So, so that means now if at all there is such a W which will be able to simultaneously satisfy all the constraints, then we will be able to, that is, if we formulate it like this, then we will be able to like get such a W which satisfies all the constraints as well as minimal, and as well as minimizes this L2 norm, right? And but we have assumed that the data set is linearly separable. That means there is such a W which satisfies all these constraints, right? So then, what happens? So then we let us write the whole thing as a like in the using the augmented objective function, which brings us something like this. Okay, so instead of the these alphas are basically the Lagrange multipliers which we talked about. Forget the b's. So now what we have to do? We have to, so we have the W is an unknown, and the all these Lagrangian multipliers, these are also the unknown. So what we'll do is we'll start off by differentiating. We'll take the partial derivative of the loss function with respect to all the unknown quantities and equate them to 0. So that will give us some simultaneous equations which we'll have to solve. Now, so before going into that, let us also note one thing. So this is basically, like, this part is basically ensuring correct classification and this is basically you can see the similarities between this thing and what we did in ridge regression. So ridge regression you have studied, right? You know what is ridge regression?
Yes, sir, it has an L2 regularizer.
Yeah, right. So it is a ridge regression is basically linear regression along with the L2 regression. So in case of normal regression, the loss function is this, right? This is the loss function, the standard OLS loss function. Now in case of ridge regression, the loss function becomes we have a parameter lambda, and this 2 is kept because when you do the derivative, this the squared, this 2 will come down so that you can just cancel it. So so basically some constant times are the L2 regularizer. Okay. And so do you know why we go for, or what is the need of keeping this L2 regularizer in case of ridge regression? What is achieved by this?
To prevent overfitting, like
Yeah,
the
to
values of W cannot explode there.
right, right. So to basically, I do not want the values of W to explode. So, so this regularizer, it makes sure that the magnitudes of all the elements of W are are not too high. They are like bounded, you can say. So like it's like saying that so this is basically so there is something like a circle, and like all the values of it remain within the circle. So you can say something like, so normally the equation of a circle, as we know, is x1 or x1 minus a square plus x2 minus b square equal to r square, right? This is the equation of circle which we know. So like if you now consider the center a, and like the center of the circle to be the origin, which will mean that the a and b are basically zeros. So then it becomes a case of x1 square plus x2 square equal to r square, right? And what is x1 square plus x2 square? This is nothing but the squared L2 norm. So it's like say, and that is precisely what we are talking about. So like basically we are trying to like make sure that that is we are trying to define a circle so that all the elements of W remain within that circle, and we are trying to minimize the radius of that circle also. So that is the idea. So we are trying, that is, as you said, the aim is to make sure that the elements of W do not explode. So that's like in this case also we can say that we are doing, that is this loss function. So although we reach this loss function from a different way, we are looking at it from the perspective of margin maximization along with certain constants. It can be seen in a different way also. We can just say that we are trying to, that instead of calling this as the loss function, we can call this as the loss function. And then accordingly, we can also add a regularizer onto it, just like we did put the regularization on the in case of linear regression. So this is like, you can say it's an alternative view of the support vector machine. So like in which case we will call this as a new loss function. And so this part is so basically what this part is doing is that it is ensuring the correct classification, and this term is ensuring that is like it is regularizing the W to by preventing the overfitting, as you said, so that by making sure that none of the elements explode. So that this term is sometimes called as the empirical risk, and this term is sometimes called as the structural risk. Okay. So like this is just an alternative view of the SVM classifier. I mean the max merging classifier. Okay, so now we were earlier talking about that we will do the derivative. So we can take the derivative of this loss function with respect to W as well as with respect to the alphas. So let us see what happens if we take the derivative with respect to W. So first of all, so W is of course a vector, and this loss function, as you can see, it's a scalar. Now we can differentiate a scalar with respect to the vector according to the following rule. So let us say W is so the general rule is as follows. X is a vector, scalar, W is a vector. The result is going to be a vector which is like this. Okay, so so it's nothing but taking the derivative of the scalar quantity with respect to the individual elements of the vector. Okay, so that is how we do the vector differentiation. Now they are like in for certain so now in general, of course, this x will be some function of x of W, that is x is equal to some fw. So for in various situations, you can like there is some standard forms are there. So just like you know that in case of normal differentiation, there are certain standard forms like d of x square with respect to dx is nothing but twice x. So similar rules are also there in case of I mean similar formula are also there in case of vector differentiation. So I mean the and the vector analogy to this is that is this L2 norm square. You may convince yourself is nothing but W transpose W. That means the dot product of W with itself. Okay, you can convince that they mean the same thing. So like basically we are doing taking the dot product of W transpose W with respect to W. So this is a scalar and this is the vector. So you can just actually work out this formula and convince yourself that what you will get is nothing but 2w, okay, which is the vector. So that is the so that's a standard formula. That's what we will follow here. So let us try to see what happens when you apply that formula in this case. Okay, so in the first term, we have the squared L2 norm. So half comes out and we apply the formula which I just mentioned. So like you will get twice W plus. So the first term here is simply the summation over the alpha i's. The second term is yi alpha I W transpose xi. Correct? So this term clearly does not contain W. This term does contain W as W transpose Xi. So these things are all like constants. So the Xi is also constant. So it's just this term is linear in W. So it's just again just analogous to the normal differentiation. The derivative of this part is just going to be minus yi alpha I xi. Okay, since it's a linear term, the w just drops out and this is what we get. So half cancel. So we get 0. Okay. So we equate it to 0. So that means w is equal to alpha I yi xi. Okay. So this is the this is like the first important relation we have obtained here. That is the whatever value of w we will get, the max margin classifier which we will get, that should satisfy this relation. Of course, the alphas I do not know, but once I get the alphas, the final solution of w must satisfy this relation. Okay, and you can just do this basic sanity check. Alpha is scalar, yi is scalar, and xi is a d-dimensional vector. So it's like a d-dimensional vector multiplied by scalar, which is of course still a d-dimensional vector, and you are adding up n of them, so you are basically getting another d-dimensional vector. So w will be a d-dimensional vector. Okay, so that's that's consistent. Now, so this is one relation which we have got. The next part is of course to do the differentiation with respect to the each of the alphas. So we would do the derivative with respect to, let us say, alpha I. There are n number of alphas, so we have to differentiate with respect to each of them. So if you look at the first one, it's like this one does not have alpha, so it will just disappear. This one, like with respect to like for alpha I, the derivative will be 0, sorry 1, and for all the other values of alpha apart, that is like alpha 1, alpha 2 up to alpha I minus 1, alpha I plus 1 to alpha capital N, all will be 0. Only the derivative of alpha I will be 1, right? And minus, again the same thing, like for only for the ith point I will get correct. For all the other points, they like for all the other data points, this will be a constant with respect to alpha I, so the derivative will just disappear. So this is what I will get. Okay. So So now what we are going to do is, but as you can see, the expression which we get like this, like it's another expression in terms of W, it does not contain any alphas. So what we are now going to do is, we will do a replacement. Whenever we got this expression for W, this expression is not going to be of any immediate use to us, because like as you can see, that is, there is not much we can do with it. But here what we have got is, we have got an expression for W. Okay, so what we will do with this expression is that, we will in the objective function, wherever we have W, we will plug in this thing. Okay, so it will look like this. So here we have, in this term, what I have is the L2 norm of W square. So that is equal to W transpose W. And I have already found that W is equal to alpha I yi xi. So W transpose W, I will write it as alpha I yi xi transpose correct. So now once I write it, I can it will become like a bit messy expression. So I am not going into the details of exactly like how it will is going to work out, but it's messy, but it's straightforward only. So like, in fact, you can understand that it will be something like this. So basically we have n like, this is a summation of n terms, and this part is also a summation of n terms. And so like, basically it will be like a so basically we'll have to do n square number of products we will get, and we'll have to add all of them up. So each of those products will look somewhat like this: alpha I, alpha j, yi, yj, xi transpose xj. Okay, this is how the whole expression will look like. Okay. So finally, what we will do is like, we will plug in this expression, the expression which we got, we will plug it into the yeah, we will like plug it in, so, and in the original expression, and we will get a I mean a new objective function which will look somewhat like this. So like, we will get a new set of constraints also. So of course, I mean, if we are writing the alpha sorry, see, like, since we are writing the w's as by bringing the b inside the w, the bias term inside w, it will look somewhat different. But anyways, by the way, so so this is one term, and so here there is another w, and the w transpose xi terms. So here also similarly, I will replace the w with the term which is like with this particular term. So again, like, you will see something else happening. And so finally, like after a lot of these like a lot of things like this, you will get like a new quadratic function which will look somewhat like this. That is that is, you will get an objective that is like, basically what we have done here is that, earlier we had an objective function in terms of both w and alpha. Now we have got rid of those w's entirely, and expressed is as a quadratic I mean, as a equation or objective function only in terms of the alphas. Okay, And so like you will see, if you do the full substitution here, you will get this kind of a new new optimization problem. And this is so like this is left as an exercise for you to work out, like that is what happens if we like do all the substitutions, and that is these w's we like in case of this w also we put in this thing and so on. So ultimately, what you will, let us just say that you will get this kind of a new problem. This is called the dual problem. So the like the original problem, this is what is called the primal problem. This is in terms of W. Okay, see, alpha is not there at all. So we just like have the original problem, which is called the primal. That is a problem in terms of W. Now that same problem that is expressed in a different way in turn. Now W is gone. We have have it a problem only in terms of alphas, and that is called the dual problem. Now the good thing is that this actually fits into the standard form of a particular kind of approach called quadratic programming. So quadratic programming is like is a situation where you have like so okay, so as you can see that this is basically a quadratic expression, that is you have alphas multiplying with each other, and along with it these constants are there. I mean yi, yj, xi, xj, these are all constants. So so this is called a quadratic programming. And then when we like do so we do not really have to solve it separately. There are solvers for solving this quadratic programming. So when we solve this kind of a quadratic programming, I will be able to get the values of alphas. Okay, so basically the alphas will be coming out directly. And once I get the alphas, then since I know that like w can be expressed in this form, that is I can just I can just plug in the values of alphas. Yi, xi I know anyway. Yi are my the labels, and xi are the feature vectors. So I just write w in this particular way. Okay. And it will also turn out that for most of the points, so note that alpha is present for each of the points. For every point we had a constraint, and along corresponding to that we had a Lagrangian multiplier. So it will turn out that for most points the Lagrangian multiplier will be 0. The only for the remaining points for which alpha is not 0, that is those are going to be called as the support vectors. So W, we can say, is actually a linear combination of those support of a small number of points only, which we'll call as the support vectors. So like for example, let us say that n equal to 20, out of which the only alpha 12, alpha maybe 8, alpha 17, and alpha 18, like these are not 0, the rest are all zeros. So in that case, the W hat which we get will be equal to just alpha 8, y8, x8 plus alpha 12, y12, x12 plus alpha 17, y17, x17 plus alpha 18, y18, x18. Correct? So the remaining points become irrelevant. Only W is defined only in terms of the small number of points, which are called as the support vectors. And these are the points basically on which W is supported. Okay, so that is why they like these x 12, 17, 18, these are all feature vectors, and they support W. So that is why they are called as the support vectors, and the W is called the support vector machine. And once we have this support vector machine, we will do the prediction on any test point in the following way. That is, we will have the like in the normal way we do the testing like this. W transpose X test. Correct. But what is W? W, as we know, is this thing. So, so it will basically become sine of summation I equal to 1 through n alpha I yi xi whole transpose. So like these are of course constants, so transpose does not matter. Xi transpose X test. Okay. So if you look at this expression, what is happening is that basically we are taking the dot product of the test vector with each of the support vectors. I mean, for the other vectors, of course, this alpha is 0, so we can just ignore them. Taking that dot product is useless because the product is going to be 0 anyway. So only with we will take the dot product of the support vector of the test vector with the each of the support vectors, and we will multiply them by these constants, and then we will just add them up. Okay, so the important thing to note is that what we are doing for prediction purpose, what I am doing effectively is I am just taking the dot product of the test vector with each of the support vectors. So that is this is a crucial idea which we will come back to it in later in this class. Okay, so this is the basic idea of the support vector machine, and it will give you
Sir,
like yes.
how did we get the constraint for the dual problem?
So the constraint for the dual problem, like you will understand it like once you write down the actually do the all the derivatives and also bring in the that is once you do the replacement of the w's in the primal problem, like you will see. I mean, there is also like in this sorry in the original problem also, like you will that is the by doing one derivative, like you will get some expression. So all that details I have not shown here, but you will get it once you do it. I will share.
Okay,
I'll
sir.
share one. I'll share one thing where the entire thing is worked out for you. Okay, so at this point we'll take a break and for 5 minutes. After this we'll continue.
Sir,
Yes,
hello. Sir,
yes.
I have a doubt related to the assignment.
Huh.
In the decision tree assignment, do we have to implement decision tree from scratch,
No,
or
no, no,
can we
no, no, no.
use built-in libraries?
Yes, you can use built-in libraries.
Okay, thank you, sir. Also, I had another doubt. In the ridge regression, how does like adding the regularization term? You said that if we add regularization term, the W weight values will not explode. But
Yeah.
how does that ensure that overfitting will be removed, will be prevented?
Yeah, so basically what happens is that so suppose you have a situation. One second. So suppose you like basically you are expressing y as W transpose X. Okay, so that means what? That means you are like every element of W is to be is acting as a weight for or coefficient of the different features. Okay, now suppose it might so happen that one I mean, as of now, there is no there is no constraint on W. W can be anything. So let us say that you have somehow reached a situation where some values of W are very large. Okay, let us say that W1 is equal to say some 10,000, W2 is equal to say 0.1, and W3 is equal to maybe minus 12. Okay. So now, and correspondingly, you have some feature vectors x1, x2, and x3. Now, so suppose there is some like there is some kind of error in the first feature vector. I mean, the first feature. Now, whenever I am measuring the feature, there can always be some amount of errors. So suppose I like instead of measuring x1, I get it as x1 plus epsilon. Okay, where epsilon is a is the error. Or let us say that all of them have got some errors. X2 plus epsilon, x3 plus epsilon 3. And let us say these epsilon are like roughly something like 0.1. So and the xi's are also, let us say, something like in the order of say like 10 something. I mean 10 to the power 1 or something. So it's like about 1% error. That's not much. But now what has happened is that because the first coefficient is very large, is 10,000, so this small error will blow up. That is because the W2 and W3 are relatively smaller, so these epsilon 2, epsilon 3, I mean, they will be multiplied by their respective coefficients, but because the coefficients are small, it's not going to blow up. But here, what has happened is that this particular error has blown up. Like, so you will get the perturbation it will cause on Y is really large. So that way, so that means that like so basically it's like a, so this is kind of situation we are calling as overfitting, because on the training data set which you have, which like ostensibly did not have the errors, you have been able to do the prediction perfectly. But now once you get an out of training sample example, where which is only a slight perturbation of the training examples, you are like your Y is like just like very different from what it should have been. Right, so then we are basically we because of a small error in one of these in one of these features, the Y, our prediction of Y is becoming very bad because of the corresponding weight is so large. So what is the solution? The solution is to make sure that none of the coefficients or none of the weights become very large. That is, I would like to do well or fit well that on the training set, while also making sure that none of the W's become large. So that is what I hope to achieve by putting this regularizer called L2 square. Okay.
Yes, sir. Thank you, sir.
Hello, sir.
Yes.
Yes, sir. I have one question, sir. Max margin classifier and SBM are both same.
So it's so is so like yes, you can say that the like practically they are the same. So, actually SVM is a slightly more sophisticated formulation of the max margin formulation classifier than what we have seen right now. In fact, that's what we are going to see immediately after this. But what we have seen so far, that that is that also you can call as SVM. So so that is actually called as a hard margin SVM, a special type of SVM, which is different from the original SVM. But it's still, it can still be called an SVM. Okay, let us now continue. Just give me a second. Okay. So now, so we have assumed that the data is linearly separable. Okay, that means there does exist a W such that all the cross points are on one, or the plus points are on one side and the minus one points are on the other side. Now let us consider the situation where the data is almost linearly separable. So what does that mean? That means that there are a small number of outliers. That means on this side there are a few circle points, and on this side also there are a few cross points. Okay. So in such a situation, so that means what? That means except for these, so I will never be able to achieve 100% accuracy here, like with any linear classifiers, because the data is not perfectly linearly separable. However, we also know that except for a small or number of outliers, the rest of the points can still be correctly classified. Okay. So now what do we do in such a situation? The idea is, of course, to make sure that, okay, so first of all, let us go back to the original condition, I mean the original SVM formulation. So the problem here is, just a second. Yeah, so this is the original formulation. So the reason why we will not be able to go ahead with this formulation itself is that this constraint that all the data points are going to be correctly classified by both the marginal classifiers, this is no longer true, because we know that we have assumed the we have assumed the presence of some outliers for which this is not going to be correct. Okay. But so then you may say that, so what's the problem? You just you just don't write this kind of an equation for the outliers, and for the remaining points you write this equation. Then all the problem is solved. But the issue with that is that we do not know which are the outliers. In fact, the which points are going to be outlier depends on which W you are choosing. Remember that we have not fixed any value of W. W is something we have to find out. W I will choose in a way to find the to maximize the margin. But if like for one choice of W, some points may be outlier. For another set of choice of W, some other points may be outlier. Say like this. Right? So suppose I choose the W like this. Correct? So in this case, this point and this point, these are the outliers. But suppose I choose W to be like this, then I find that only this point is the outlier. So for some other choice of W, maybe some other point might be an outlier, right? So like if I choose W, like say like this. So then in that case, only this is going to be an outlier, and so on. So that for the choice, so I do not really know a priori. So like like if we look at consider the different points, the initial set of points, there is no way to say a priori which one is the outlier and which is not. It really depends on how you choose the W. So we cannot just drop this constant for some points and go ahead with the rest. So what we have to do is we have to take into account the possibility that every point is a potential outlier. So what we really do is as follows. So this was the original constraint we had, right? This is saying that all the points are going to be correctly classified by the by both the marginal classifiers. Now what I am going to do is I will add this kind of a slack variable. That means that there might be some points for which this equation is not satisfied. That is like for example, this part, the left hand side, for some points may be something like 0.5 or maybe something like -3, in which case this equation is violated. So now to ensure that this equation is still intact, what I will do is I will add some quantity on the left hand side. I will write it as 1 minus xi I. So these xi i's, these are called the slack variables. Why they are called slack is that if this is correctly classified, then the xi I is not needed. Then I can just assume that xi I is 0. Okay, if this happens, then xi I is equal to 0. But if it does not happen, say if this side is 0.5 and this side, so 0.5 is clearly is less than equal to 1, or -3 is less than equal to 1. So in that case, the xi i's will become important. So in the first case, what I will say it as 0.5 is greater than equal to 1 minus 0.5. Okay, so I have basically put xi I equal to 0.5 in this case. Similarly, if you like in the case of -3, I can say that -3 is 1 minus 4, right? So xi I is equal to 4. So of course, like xi I can be something else also. That is, it need not be 0.5. It can be say 0.7 or 0.8 or 1 also. But this is the minimum value of xi I for which this is going to be satisfied. So why do I want minimum value of xi I? I mean, ideally, ideally xi I should be equal to 0. That is, in which case it would be perfectly solved. But but if that is not happening, then I will bring in this xi I. I will as close to 0 as possible, just to make sure that this happens. Okay. And you can understand that xi I, there is no possibility of xi I being negative. Xi I will always have to be positive, because this is a greater than equal to constant. So like so making xi I negative will not solve any purpose. So xi I will have to be as close to 0 as possible. So which basically means that xi I will, like, I am looking for the minimum possible value of xi I in all cases. Okay. So the geometric, so like we can try to understand the geometric interpretation of these xi i's. Just wait for a couple of minutes before that. So basically xi I is equal to 0 for all the points which are correctly classified anyways. And for those points which are not correctly classified, I will have some non-zero value of xi i's. Now among those points, there are two groups of points. For ones for which this is positive and positive but less than 1, and then there are points for which this point is a negative altogether. So to understand what that means, so again come back to the original example. So so there are the red points which we are calling as, let's say, -1, and the blue points which we are calling as +1, just like earlier. And then we have these kinds of so let us say this is the optimal, the max margin classifier, and these two are the marginal classifiers. Okay. Now consider this like these points. Okay. So so as you can see that these are lying right on top of the marginal classifiers. So these are the points through which the marginal classifier passes. So like it can be shown that actually it's these points which are the support vectors, the points for which alpha is greater than 0, alpha is not equal to 0. For points like this which are away, for them alpha is equal to 0. Okay, this alpha is equal to 0. So but here alpha is non-zero. Okay. So these kinds of points are the support vectors, because the hyperplane or the max margin classifier is really supported by these vectors. Now, but the support vectors, I mean, they are, but they are still correctly classified by the hyperplane, by this W, which classifier we are which we are considering. They are on the correct side. About that, there is no doubt. But they are sitting on the marginal classifiers. But if you, in contrast, if you look at this point, here you can see that this is actually not correctly classified by the marginal classifier. Okay, and it is still correctly classified by the actual classifier. I mean, the actual classifier has reds on this side and blues on this side. So this is red and it is on this side. So this is correctly classified. But with respect to the this marginal classifier, it is not correctly classified. Similarly, if you consider this one, say later, if we have a blue point sitting here, this one will be correctly classified with respect to the the main classifier, but not correctly classified with respect to the this marginal classifier. Okay, so this is correctly classified with the main classifier. What's the main classifier? The main classifier is W transpose X equal to 0. So that means what? That means if you consider for this point, so let us call it as X5, let us say. So Y5 W transpose X5 is greater than 0. Correct? But this is not, if you consider this classifier, the marginal classifier, which is W transpose X plus 1 equal to 0. Right? So if like, so like for so for points like this, so for for most of the point, so for the points in which for which it is correctly, sorry, just a second. So these points, they are all -1 points. So, and they are correctly classified with respect to the this marginal classifier, but this one is not correctly classified with respect to the marginal this marginal classifier. So we can say that like Y5, now Y5 is of course equal to -1. This one is misclassified, right? Because it's so this product becomes less than equal to 0. Okay, so that means what? That basically means Y5 and W transpose X5 is less than minus Y5. But what is Y5 is -1, so minus Y5 is 1. Okay, so it's basically saying that Y5 times W transpose X5 is less than 1. It is greater than 0, but it is less than 1. Okay, so like earlier we were considering this kind of points for which this quantity might be something like 0.5. So this is an example of a point for which this is an example of a point where this thing, this product Y5 into W transpose X5, this might be something like 0.5, because on one hand it is greater than 0 because it is correctly classified by this plane, this hyperplane. On the other hand, it is less than equal, it is less than 1 because it is misclassified by this marginal classifier. Correct? The similar story for this one also. You can just verify. So there are some points like this which are correctly classified by the optimal classifier but misclassified by the marginal classifier. And then there are points like this which are misclassified by the the main classifier itself. That is, for them Y5, let us say this point is X12. Okay, so for this y12 times w transpose x12 will be a negative. It means that it is not only is it misclassified by the marginal classifier, but it is also misclassified by the main classifier itself. Okay, so for such a point, this left hand side may actually be something like -3. So the slack variables will have to be adjusted accordingly. So for this point, the slack variable will be will be positive, but less than 1. For this point, the slack variable will have to be greater than 1. And for the remaining points, like which are in like which are for which there is no problem either with the marginal classifier or with the main classifier, for them the slack variables will be 0. Then I will rewrite the original constraint optimization in the following way. I want to minimize, so the structural constraint remains so the max margin constraint remains like unchanged. The constraint equations have changed like this. So like I can no longer say, so this was what I was originally saying, but now of course to include the outliers like this, I have to include the slack variables. So this is like what I say now for all the data points. But at the same time, but I have also noticed that all these slack variables, they cannot be negative. They will either be 0 or they will be positive. So this becomes an additional constraint for us. Furthermore, I do not want all the that is, I do not want the slack variables. I will ideally want the slack variables to be, I mean, I do not want any outliers. Ideally, I want there to be no outliers at all, so that all the points can be correctly classified. If that does not happen, then of course I want to minimize the number of outliers. So what I do is I put in the total summation of the slack variable xi in the objective function to make sure that this is also minimized. Okay, so minimizing the sum of the xi's is like you can say is a proxy for trying to reduce the all the outlier points. It's not exactly the same. I mean, there can be situations where there like there is like there might be several outliers which are for which I need small xi's, or there might be only one outlier for which I need a large xi. So this is like in a sense, it's not really trying to minimize the number of misclassified points, but it's actually trying to to minimize the total margin of misclassification. But it's still used as a proxy term because it is like easier to deal with mathematically. So basically the idea of this is that I reduce the outliers on this is to make sure that like all the points are like correctly classified, we like relaxed by the outliers, and this is like this is like purely for technical constraints, for that the xi cannot be negative. Okay, so we have the new set of constraints. So so we again put them back in the standard form. So the standard form of the constraint is that the like gi w will have to be less than equal to 0. So this again I write it in that form. So it become, I rewrite that as 1 minus xi minus yi w transpose xi, forget the b, is less than equal to 0, and this I write as minus xi is less than equal to 0. Fine. So this is my new these new set of constraints I absorb into my main objective function with the help of the Lagrange multipliers. So note that now there are two sets of Lagrange multipliers. For these I have the Lagrange multiplier alpha I, and for these I have beta I. Okay, so I get this kind of a like augmented loss function. So now the unknowns are the w's, the alphas, and the betas. Okay, also the size. So now I have 4 sets of unknown parameters. So now what I will do, like the same thing which I had done earlier, that was only I will do. I will like take the derivatives of the w's, the x's, alphas, betas, etc. I will like take the derivative once again. So so this time also I am not going to show all the steps of the derivative. But one thing is you can see right away that when we take the derivative with respect to w, I will still get the same expression. That is, for w I will still get just like earlier. So this part will become w, and here this part will become the summation over ai equal to 1 through n. This part will become alpha I yi xi. Okay, this is just like what we had earlier. So so this expression will remain unchanged. The problem lies in the calculations of these alpha i's. So you will like the also of course we have the additional xi i's, etc. So the calculation the calculation of w will not change, but the calculation of the alphas will change. So we will again get this kind of like once you once you have the that is once you write the zeros, I mean carry out the partial derivatives, equate them to 0, etc. You will get get another quadratic programming problem with the in terms of the alphas after eliminating the w's, the x's, and things like that. So again, I will not go into the details of that, but finally you will be able to get the alphas by solving the dual problem using the QP, the quadratic programming. And this time also alpha will be sparse. That means what? For most of the data points, alpha will be 0, and only for the support vectors, alpha will be non-zero, just like earlier. Apart from the alphas, when you solve this problem, you will also get the x's, and you will see that for the points which are lying on the marginal classifiers, that is the support vectors, for them the xi's are 0. Then there are points which are lying between the marginal classifier and the optimal classifier. That is, the optimal classifier correctly classifies them, but the marginal classifier misclassifies them. So for them, xi will be between 0 and 1. And then there are points which are completely misclassified. That is, they lie on the wrong side of the optimal classifier itself. For them, xi is positive. Okay. So this is the actual or the full formulation of the support vector machine. It is sometimes also called a soft margin support vector machine because of the presence of the xi-i's. Soft margin in the sense that we are building a margin, but we are also allowing for a small number of outliers to percolate the margin and go beyond, go to the wrong side. That is, for example, this point, this has gone through or infiltrated through the margin and gone to the wrong side. This kind of situation would not have happened in the earlier formulation which we dealt with, because that assumed that all the points are going to be correctly classified with the optimal classifier. So this is what you get, like this is the support vector machine formulation, and like till the advent of the till the advent of deep learning, this support vector machine was considered as like the strongest or the most powerful classifier which we have in machine learning. Now let us come to another situation where the data is non-linearly separable. Okay, so what, like this kind of a situation. So what does this mean? This means that there is no linear structure which can separate the two classes of the data. That is it's useless to use the to go for the soft margin formulation also. There are simply, I mean, like there are simply too many outliers which I mean there are too many misclassified points to be just dismiss them as outliers. Okay, so there is no point in no single linear structure which can separate the 2 points. But there does exist a circular structure like this, which can separate the 2 points. Okay. So we may say that the separating, so if the this point, the center, like let us say is x naught, and the radius of this circle, let's say is r. So we can say something like this as follows. So the structure of the, the equation of the circle can be called as x minus x naught transpose x minus x naught equal to r square, let us say. So instead of writing r square, I can just write it as r. It's like that is the square I just absorb into the r. So so like why? So this is the equation of the circle. So in case you are wondering how this became the equation of the circle, you can just remember that like you may write the equation of the circle like this. This is the familiar form of the equation of the circle. But this is nothing but okay. You can like you can just verify that this is correct. So it's like any point I am expressing it as a vector x1 x2, and the origin of the circle, I mean the center of the circle, I am expressing as the vector a b. So I am just taking the difference between the vector difference between these two vectors, and then doing the transpose. You can just verify that this expression is the same as this expression. So it will be something like x1 minus a, x2 minus b, this vector transpose x1 minus a, x2 minus b. And so like it's like it's like one vector transpose that same vector. So that basically means you are taking a dot product of each of the elements. So you will get x1 minus a whole square plus x2 minus b whole square, that which is exactly what you have got here, right? So like this, so the equation of the circle is by, so this x basically denotes the like any point on the space. This x naught is the center, which is the like the central vector, and so this is what it becomes. So this is the equation of the circle. Okay. So for the points which lie on the circle, this equation is satisfied. For the points which lie outside the circle, the left hand side is greater, and for the points which lie, that is outside the circle, means x minus x naught transpose x minus x naught is greater than r, and inside means the same thing is less than r. Okay. So the we can so assuming like if we call these blue points as +1 and these red points as -1, I can design the classifier as in the following way. That is y is equal to sine of this thing. Okay. So as you can understand, for those points which are outside, this is going to be something greater than r. So this part, once you subtract r, you will get some positive quantities. Taking the sign, you are predicting +1, and which is of course correct because all the +1 points are outside the circle. If you consider any point inside the circle, so this part will be something negative, something less than r. So once you subtract r, you will get a negative quantity. You take a sign of that, you get -1, and the -1 points are all inside the circle. Okay, so you can see that this is the valid classifier. And But now you will see a trick. The trick here is that once you expand this x minus x naught transpose x minus x naught, this is what you get. Okay. So now let me define a quantity called phi x. Instead, so x is of course the like any vector in that space. So I define phi x as follows: x transpose x minus 2x and 1. So clearly phi x, it's a 3D vector. This your x, it might be any dimensional. X may be d-dimensional, but phi x is 3D. Sorry, it's not 3D. It is this is 1. This is also 1, and this x is d-dimensional. So it is d plus 2. Okay. So x is rd. Phi x is rd plus 2. This is scalar, and x is like just the original vector x multiplied by this coefficient of 2. Okay. Similarly, I define w as 1 x naught, which is the center of the circle, and x naught transpose x naught minus r. Okay. Now if I write w transpose x, then what do I get? You can just verify that I get x transpose x minus 2x x naught plus x naught transpose x naught minus r, right? Which is the same as x minus x naught transpose x minus x naught minus r, right? So this is the circle. This is actually precisely the circle which we are dealing with earlier, right? So that circle, so now the classifier becomes if w transpose x. So basically now we are dealing with sign of w transpose, sorry, not w transpose x, but w transpose phi x. W transpose phi x, correct?
Sir, here W is always belongs to R power 4, right?
No, it depends. W is something that depends on that is it all depends on what x is. So in this case, x I consider as it's a two-dimensional structure, but in general x is d-dimensional. So in that case, W will become like x transpose x minus 2x and 1. So just two more dimensions. So x is anyway there. That is, so d dimensions are anyway taken care of. Additionally, two more dimensions. X transpose x is a scalar, 1 is a scalar. So two more dimensions. So yeah, it will be R4 only if d is equal to 2. So now what the thing is that if we consider, so this is, as you can see, this is actually a linear classifier with respect to phi x. So, but phi itself is a nonlinear transformation on x. Nonlinear I am saying because it involves this quadratic term x transpose x. So in terms of x, this circle which we considered, this circle, this is definitely a nonlinear classifier. Nonlinear classifier on x. But if we consider this one, it's the same thing, the identical thing as the previous one, but this is now a linear classifier on phi x. Okay, so basically that means
Sir,
what?
shouldn't it R square according to circle of equation?
So it should be equal to r square, but I am just considering, instead of considering r as the radius, I am considering root r as the radius, so that it becomes like the r square becomes r. That's just a matter of nomenclature. That is this capital R which I have written is not the radius but the squared radius, you can say. So what I have gotten is, that is, if I am able to transform the data itself, the x vectors themselves, they are non-linearly separable. But if I transform them to a new space called phi x, in that space I can classify them with the help of a linear classifier. Okay, but the transformation itself is non-linear, but once I make the transformation, then a linear classifier like SVM or perceptron, etc., can work. So but the problem is how to get this transformation phi x. So in this case, because I knew that the data was organized in this particular form, it's a two-dimensional system. I can plot and I can see that I can come up with a circle and something like it. But in general, of course, it will not be this will not be the case. So in general, I will not be able, because of the specific case that I know that a circular classifier can separate the two classes. I wrote phi x as in terms of the circle. In general, I will not be able to do that. So basically, what I have to do is I have to get some kind of linear transformation on x, which I will call as phi, such that in the space of phi, the phi's are linearly separable, and on that I can run the something like the max margin classifier. So if I have to do the max margin classifier in the phi x, this is what it will look like. Okay, it's like only instead of everything else remains unchanged, the only change that happens is that wherever I had xi, I will replace it by phi xi. I will do that in the in the equation, in the dual formulation also, and when I am doing the classification also later on any test point, there also I will do the same thing. So note that in the if you now remember, I had made a point earlier that these in the objective function, they appear as dot products, and in the where we are making the prediction, there also we are taking basically the dot product. In the objective, we are taking the dot product between various pairs of the vectors, theta vectors, and in the while making the prediction, I am taking the dot product of the test vector with each of the support vectors. Okay, and now now the only thing change I have to make is that I have to replace this by the phi's. Correct. But the problem is, of course, that I do not know what is phi. I cannot I cannot calculate what is phi. Like in this specific case, I actually showed you what phi can be, but in general, I will not know it. So what will I do? I will apply what is known as the Karnell trick. The Karnell trick is that I will actually not find phi, but I will find these I will be able to calculate these dot products. That is, I do not know what is phi xi. I do not know what is phi xj, but I know what is phi xi transpose phi xj, and that is equal to some kernel with some function capital K of xi and xj. Okay, so this capital K, this function is what I call as my kernel function. So it's like saying that the kernel function, it parameterizes the dot products between the xi and xj in the phi space, even though it does not it does not take the phi itself, it does not utilize phi itself. So that is a very strange thing which I am saying. I am saying that this will hold even though I have not defined what is phi. So so that might sound like quite absurd or nonsensical, but actually it is not. So it can be say like what there is this theorem called the Mercer's theorem, which basically says that if you there are certain functions okay, there is a Mercer's condition. So those functions capital K which satisfy that condition, they are all valid kernel functions. That means what these so these are all binary functions, means it takes these functions, they take two things, two vectors as input, let us say xi and xj. So if this function satisfies this Mercer's condition, that means that there exists phi such that kxi xj is equal to phi xi transpose phi xj. Okay. Even though like I may not know what that phi is, but this much I know that if this K satisfies certain conditions, then there does exist some phi which I don't know for which this will happen. So now, so what is that condition? That condition is written here so that you can just read. I am not going into the details of that. And but there are certain, that is, people have found certain functions which do satisfy this condition. So the most trivial case is just the linear function where k of like let us say we have two vectors like xi and xj, and the kernel and it's just the dot product of them, xi transpose xj. So this is like the trivial case. In this case of like, as we can understand that phi x is equal to x itself. Similarly, there is a polynomial kernel. So suppose it takes in two vectors xi and xj, and it calculates this thing. That is, it calculates xi transpose xj, the dot product between those two vectors, plus 1, and then to the power d. Because d is some degree, maybe 3 or 4 or whatever. So this is called the polynomial kernel. And then it can be shown that there exists such a function for which like you can actually express it as this kind of a dot product. So here you can actually play with some small values of d equal to 2 and or something like that, and see if you can actually find what that phi will be. Like for small values of d, you can actually calculate it in pretty much the same way as I calculated the phi here. But for higher values of d, that will not be an easy thing. Then the most famous is the radial basis function, or the Gaussian. This is also sometimes called as the Gaussian kernel. It is defined in this way. Like you just take the difference between the two vectors and their squared L2 norm, and then multiply it with some constant gamma and take the negative exponential of that. This is the RBF kernel. So these have all been shown to have the property to satisfy the Mercer's condition, and which means that there does exist some phi, that is some nonlinear transformation of the vectors for which the this function will be equal to the phi xi transpose phi xj. Okay. So basically, so where does it take us? What does this benefit to us? So it benefits to us that whenever we come across any dot product between the data vectors, I just simply replace those dot products by the kernel function between them. So in the SVM dual problem, where I initially had say xi transpose xj. So I replace that by phi xi transpose phi xj, and that I am replacing by k of xi xj. Now the phi I do not know, but k I know. I have chosen it. So once I have chosen this function k, I can of course like the so xi and xj are two training data points. So I can just operate the function on it and I will get some numerical value. Like that's all there is. Say so like if that is once I have fixed gamma and if I know xi and xj, I can calculate this thing, right? So that way so like then basically these yi yj, these are known, these kxi xj, these also I can calculate. So it's basically just reduces to an equation of the I mean a function of only the alphas as it was earlier, so I can solve it. So the solving it will give me the alpha. So then while I am doing the testing, that is for any given point x test, I will, instead of calculating phi xi transpose x test, I will simply calculate k of xi comma x test. Correct? So I'll get this. Fine. So so this also I can calculate easily. So the question might arise that which like I said that there are like different things like different functions like this which satisfy the Mercer's condition, that is they are all valid kernel functions, that is they have some phi corresponding to them. So which will I choose? So there is no clear answer to that question. So people typically try out different values of the kernel function and see which gives them the best result. And some of those kernel functions themselves will have some parameters like this one. This small d is a parameter. Now, should I go for d equal to 2 or d equal to 5 or what? Or in this case, what value I'll go for the gamma. So these are things which the users can choose. So people so there is so these things cannot be decided in advance. So the like as a practitioner you will have to choose that is you will have to try out different kernel functions, try out different values of the parameters to see which gives you the best results on the training data set and the validation data set, and then accordingly you design your classifier accordingly. Okay. So that so the what we get like this is known as the kernelized SVM, and this is a very powerful method if the data is non-linearly separable. And in fact, till the advent of deep learning, say like the revolution of deep learning started in the year 2012. Till that point, this kernelized SVM was considered as like the most powerful algorithm for complicated tasks like say object recognition in images and things like that. But after deep learning became feasible due to the increase of or improvement of computing power, then people started thinking that or started seeing at least that neural network is capable of doing better than kernelized SVM for most purposes. Okay. So this is like the story of nonlinear classifiers. So this temporarily brings us to the end of the supervised learning part. And from next class, which is on next Monday, we will start with the unsupervised learning. And the classes will be taken by Dr. Manjira Sinha. After we do unsupervised learning, which will involve clustering algorithms. After that, if time permits, we may come back to some select topics on supervised learning. Okay, so thank you. We will have an assignment based on the kernelized SVM on in the lab class, which is due on Thursday. So we'll meet there. Okay, so thank you.